Okay. All right. Seems like things are recording and maybe live. And so if you can hear me and see me, toss it in the chat here. I'll make sure I am checking things out in the chat. Just let me know if it sounds good. If you've got AOS, acquisition of signal, should be all set. But want to make sure before we jump in here. All right, here we go. David Kemp says 5x5, good to go, loud and clear. Awesome. Thank you all. All right, well, welcome, folks. Good morning. Welcome to NARCon 2023, or at least this specific presentation. So this last year, if you know, adjacently about the stuff that I do, that's great. If you don't, I'll give you a quick little intro. My name is Joe Barnard, and I run a project called BPS Space. I'm actually wearing one of the shirts here that says intern. It's fun to think of myself as an intern for this project. But I run this project called BPS Space that I started a long time ago at this point to try and propulsively land a model rocket like SpaceX. I started it to get a job because I didn't have an aerospace degree or a way to work in the industry. And it's become a job in itself. It's become a thing that I do professionally, weirdly enough. And so we have a pretty big YouTube channel. There's a bunch of interesting projects going on. I'm actually working toward doing a big space shot in the next few years. And I thought that it would be cool to talk a little bit about finally completing the landing portion of this project. So I propulsively landed a model rocket in the last year, and I wanted to show you some of the development path of that. So this, a lot of these slides are just nice, pretty images, and I'm going to talk you through some of the details. And then I figure if you want to toss questions as we go in the Q&A, I can try to address them during the presentation. We can do a Q&A after as well, and I'm happy to bring up other materials or whatever. So this is a great little composite photo of, I think this is the first flight of the rocket that ended up landing. I've built a bunch of iterations of this model rocket, but this one is called Scout F. So there's been Scout A, Scout B, Scout C, all the way up to F now. This is the first flight. You'll notice it doesn't have fins. It uses thrust vector control to keep itself upright. So it gimbals the motor at the bottom. And then when it comes down, you can kind of barely see over here, there are these landing legs. Let me make sure I can move this out of the way so I can point with my mouse. So we got these landing legs down here, and obviously this flight doesn't work well, but I've got a couple of nice photos here. You'll also notice the motor hangs out very far from the back. This is an Estes F-15 rocket motor, hangs out super far from the back, and that's just our ascent motor, and we ditch it upon the time that we're supposed to land this rocket. So this is it coming in. I like to think of this as the entry burn photo. All of the exhaust goes up in the wrong direction, and you can actually see right here, this is the ascent motor that's getting ejected off by the landing burn startup. This is another photo, really compressed, so it makes it look like the rocket's a lot bigger than it actually is. But all these launches happen at dawn in the desert because I really want that beautiful light. I mean, getting the sky like that is it makes for really compelling photos. So okay, I figured we'd start off with just some pretty photos of this rocket, but why don't we talk a little bit about the technical details, and then we can get into analyzing the flights and seeing how things happened there. So this is the flight computer that ultimately ended up working for the landing, and I can talk you through a little bit about talk you through it a little bit. This is called AVA. It stands for All Vehicle Avionics, and it's a computer that has been developed over basically the last 7 years of just iterative design, trying to figure out what is necessary for this project and what is not. And it's a little tricky because this has a lot more going on here than is actually needed to land. Frankly, if you have a good IMU and a nice processor, like, you're 90% of the way there. But to give you a little tour, we've got the main processor in the center. On the left, there's a navigation computer, and that deals with all of the inertial measurements, the barometer. It's got a GPS on there. Basically anything that the rocket might use to sense where it is or where it's going, the navigation computer is doing that. And then this one over here is called TLM. And TLM takes all of this data that the MPU and the nav are processing and working with, and it has the process of beaming that data down to the ground. That is not really important for the propulsive landing stuff. These flights are about 10 seconds. If you've ever seen one of them, one of the videos that I make, it's about a 10-second flight. So like over that course of 10 seconds, you're not looking at your computer screen that much. But Ava is a pretty densely packed board of lots of little resistors and processors and sensors and things like that. Thought I would just include some nice looking photos in here of Ava, and then one more from the side. We've got all of these terminal blocks because the idea is that you want to never build another computer. I mean, that was kind of the impetus for this. Is I never wanted to build another flight computer. I wanted this to be able to serve the function that it needed to serve. So some of the decisions for this rocket end up being in service of the larger project. So I want to do a space shot. I've got a high G accelerometer on here that isn't really required for the propulsive landing stuff, but this board can certainly get it done. Okay, so moving on, the thing that makes this really work in terms of software, in terms of, I mean, software is a really important part of this project. And I think specifically the Kalman filter is where a lot of the special sauce is. This is, if you've ever heard the audio of the missile knows where it is, that's what we're talking about here. The rocket needs to know where it is. So let's look at an example here. This is our, it says GNSS-XFEL, but this is an acceleration plot of a propulsive landing. I don't believe this one was successful. I think this burned out a little early. This is from a flight one of an older rocket. But either way, we've got these acceleration measurements. Let's think about, how does the rocket know where it is? So we've got these acceleration measurements. We've also got, this is barometric data. So what you do is you measure the air pressure goes down as you go up. You can do a little bit of math to convert that to an altitude. And you find that like, yeah, okay, cool. We have a general like altitude curve for our rocket right here. What else can we use to determine how high the rocket is? Well, I said earlier, Ava has a GPS, so we could use the GPS measurements. These are GPS measurements that come in. They're fairly, low-ish accuracy, especially vertically for GPS. They're also pretty low update rate, so this doesn't work super well. So we've got like a very noisy barometer. We've got really good accelerations, and we've got not noisy necessarily, but just not high quality, data from the GPS. But what happens is we use this thing called a Kalman filter to combine all of these measurements. So the red line in the center here is the result of the Kalman filter. And this looks like an open rocket curve, right? This looks like the smooth simulation that you want from, or the smooth lines that you want coming from like a flight simulation, except this is actual flight data coming out of really noisy sensor data. And so we aren't going to get too into how the Kalman filter works, but essentially it was several months of development for this project that focuses on this filter, which basically just weighs the certainties and accuracies of different sensors and then combines them to estimate exactly where the rocket is. And if you're lighting up a landing burn, if you're trying to do throttle control, if you're trying to, do really tightly timed or coordinated events during a flight, you have to have a really high precision estimate of where the rocket is in real time. So that is the Kalman filter, and that brings us sort of to simulation. Simulation is a really big, really all-encompassing word for something that is very nuanced and has, how do I say this? There's a lot that goes into it, and we're not going to talk too much about the attitude simulation. This is the attitude simulation. It is a bunch of lines. It looks like a big pot of spaghetti. And essentially, we're working in, this is a program called Simulink. And so it's probably not worth getting too into this. This is basically all of the stuff that goes into keeping the rocket upright and trying to have the rocket touch down on the landing pad. We ultimately couldn't get the landing pad part to work, but a lot of these things would look simpler if it were just coded out. But I think the thing that is more interesting to talk about with simulation, because for years now, I've myself and other people have been able to get TVC to work, thrust vector control to work at the hobby scale, been able to keep our rockets upright and on course. I think the more interesting thing though is throttle control. So I'm gonna let this video play. We're gonna let it play a couple of times in case you miss anything. And finally, for this F iteration of Scout, I developed a throttle control system for these little black powder motors. It actually works for APCP too. It's just a little bit different because there's some slag buildup that happens. So essentially what we've got here is this high temperature ceramic material, and it's specifically a really easy to machine version of this ceramic material. So you put these two paddles in front of the motor, and then as the motor is burning, you can start to clamp those paddles down and like redirect the thrust out to the side. You're redirecting out to one side, and then there's also a channel for the exhaust to flow out the other. So you try to evenly distribute it. One thing you'll notice here too is the exhaust actually deflects to an angle. And this was my biggest concern with this throttling approach. I've tried a couple of different things. Sometimes people suggest like an iris that can clamp down on the flame. And so the biggest concern here, though, I think is side forces. It's determining when you have a little bit of an angle in your thrust output. You don't want to vector your thrust when you don't want to. You want to have total control over where it's pointed. Manufacturing was also kind of a tricky thing for these. You see, I'm not peck drilling here. I'm not retracting the drill bit, and so the pressure inside the material builds up so great that it actually fractures. So it took a couple of tries to get this right. But one more time, just before we move to the next slide, I want to point your attention to the direction of the flame. If these two clamp arms aren't coming down exactly evenly, you end up directing the flame to the side. And when we zoom in here in a second, you'll be able to see pretty clearly, like the arms are not quite aligned and the flame sticks, it adheres to one of those paddles. And we ultimately vectored the thrust. So the question is like, how much of an effect does that have? So I actually ran a ton of these tests. So here's some more footage of the throttle control testing. I think I ran in total 6 or 7 of these throttle control tests, and I'll show some plots for this in a little bit. But on each one of these, I am measuring I'm running the same profile, basically the same amount of clamping down on the rocket motor, and then measuring those things with a load cell on the side, and then just sort of seeing like how many times can we reuse the paddles, because they don't actually erode that much. They erode a little bit. You can reduce it. Ultimately, I think these were like 2 or 3 times before it becomes a problem. Another good shot of the side force here, and then I think in a second you'll be able to see some of these load cells. I've just tossed a bunch of footage in here and figured we could talk over it. 1 second. Yeah, here we go. So on the side, if you look down in the center of your screen right here, this is a load cell measuring the side force when the rocket motor has a plume that isn't totally in line with where we want it to be. And ultimately, I don't have a plot of the side forces here, but I do have a plot of the axial force. The side forces turned out to not be a huge deal. The axial force was that this is like a beautiful plot to me. This is like a work of art. So this is over the course of, looks like 1, 2, 3, 4, 5, 6 firings. One of them is a control test, which means we're not throttling it at all. We're just leaving those clamps open and making sure that the rocket motor burns in a way that we can reference against the throttle control. So the yellow line is the servo command. That's sort of it's a somewhat arbitrary value that represents how hard we're clamping down on the throttle mechanism. And obviously these steps aren't perfect. There are some discrepancies motor to motor. There are also some discrepancies build to build. So sometimes these have new paddles that have a little bit less erosion. We're dealing with like sub-millimeters of precision on the positioning of these paddles. And so, having a bounding error of like 2 to 3 newtons on throttle control isn't such a bad thing when you have this much range. I mean, we can throttle, I would estimate this is down to something like 10, 15% of the total thrust. And this was really promising. I had tried a couple other throttling methods before this. We won't get into those today, but having this much throttle control is frankly overkill. In the simulations that I ran for this specific vehicle, we probably needed about 20%, basically plus or minus 10% thrust. And this is plenty. So these are the results of the throttle control stuff. And now we can see it working. So I'm going to let this clip play a few times as well, and we'll explain what's happening here. So on the right side, you're looking at my computer screen. And on the left side, you've got the throttle control mechanism that's actually trying to throttle the rocket motor. Now, obviously, we're inside, we're not going to burn the vehicle or burn the rocket motor. But you're actually looking at the telemetry that's coming from the actual flight computer on the rocket. And so one thing that I developed for Ava is this thing called software in the loop. And this is a thing that is common among real aerospace companies and honestly way beyond aerospace as well. But software in the loop means that we trick the flight computer into thinking that it is flying. And then we take a look at the commands that it generates. We take a look at how it steps through the flight software, and we can analyze in much better detail, in a sort of lifelike testing environment, how the computer is going to perform in flight. So this telemetry, excuse me, shows all of the different phases of flight as we throttle down to try and land the rocket. You can see the throttle percentage. You can see some of the telemetry here, battery voltage, but a lot of these numbers are actually fake because they don't really matter for this. And then below it, you'll see the altitude here. So this is a simulated altitude. And then there's this blue line that shows up too, this blue line that sort of matches the yellow altitude line. And so this is how we do throttle control. Essentially, after looking at a bunch of different data from past landing tests, I came up with an ideal curve that the rocket should follow roughly to, when the motor starts up, follow this curve to get to the ground. Throttle control is kind of a weird thing when you think about it from a control system perspective, especially when you have a fixed burn time, a somewhat fixed burn intensity, and if you're trying to target a point, it gets way harder. But even if you're not, what we're doing is basically these throttle clamps are closing and opening in order to try and get us to follow that curve. And that is sort of how the throttle controller works. I want to make sure I'm keeping up with questions here. I will probably do these two questions at the end of the session. And then if there are questions that are more related to what we're talking about, we can get into those. But I'll get to those at the end of the session. Okay, the next thing that I want to talk about is landing legs. This is, I think, probably where I made the biggest mistakes throughout this project, is not dedicating more time to development of the landing legs. So legs are really difficult to get right, especially if you don't have control over, all of the aspects of the surface that you're trying to touch down on. And this is a tricky thing to know if you haven't done it before, or if you don't work with it already. But basically, you're trying to absorb energy without putting it back into the system in a way that will make your rocket spring back up. And if you're familiar with any of these previous flights that I've done, you've seen the countless times that the rocket has gotten really, really close, and it hits the ground and it bounces. It springs up and it falls over. And that's all in those legs. So this design is all right, but I'm not super proud of it. Essentially what we've got here is carbon fiber spars that are terminated by little tiny coupling points. So these are 4 millimeter carbon fiber spars in the center and 2 millimeters on the side, and those sort of support the tension of the legs. The center strut supports the compression on the legs when it touches down, and they fold out via a rubber band, which we'll see in a second. The hardware that's attaching to the rocket here is CNC'd out of just regular 6061 aluminum. And the idea was that I wanted something that would take the impact of up to 10 landings without changing its shape a whole lot. And 3D print is going to be kind of tricky to do that with. So here's some footage of these legs folding out. I've got a bunch of this that just sort of loops. One of these clips actually shows the way in which these legs fold out. If you look closely, I can actually pause the video. 1 second here. Oh boy. Okay, we're gonna hit pause. I'm gonna drag it over here. So if you look up right here, this is a nichrome wire that has heated up so much that it has burned a rubber band that's holding these legs back. Basically, the legs start off as closed like this, and the nichrome wire melts this rubber band, and that's how they fold out. So then the leg slots into place like that. It sort of locks out, spring loaded by these rubber bands that pull it down, and that is how they work. Towards the end of the program, I did end up changing this design. I added linear dampers, basically. So these are these things that are filled with oil, and they just can't move very fast. I added linear dampers to the end of the leg, and that helped a whole lot. It was really tricky to think of how we could work within the mass budget to dampen the shock of the impact, but there were these little linear dampers that I added right at the end, and those seemed to make a big difference. I think if I were doing this again, I would dedicate a lot more of my mass budget to having good legs, because you can solve bad control systems with good legs when you're landing things. Okay, we can talk a little bit about the TVC mount, or the hardware that gimbals the rocket motor. This is me milling it out. It was definitely not necessary to make this out of aluminum. I had some problems that you'll see in a little bit with wiggling on the hardware that actually gimbals the rocket motor. And so I sort of went a little crazy with just making this part as rigid as possible. So I milled out of just billet aluminum, I milled out, or I guess extruded, I milled out these parts for a gimbal mount that is all metal. And so there's like no slop in this, there's no play, there's no backlash. And that's especially important when you have these two F-15 rocket motors that are stacked on top of each other, because you have a really tricky like moment arm situation where it just wants to be spring loaded. So this was the development of the TVC mount. One of the things that I wanted to mention was the reaction wheel on this rocket. So this is probably something that I would cut if we were getting really tight on the mass budget and needed to, have something elsewhere. The reaction wheel controls the roll axis. It basically spins up or down the rocket. It's made out of aluminum for the first flight, and then I started replacing as many parts as I could for the subsequent flights to conserve mass. And then you can see what happens here. Basically, the wheel spins up, and it spins up the rocket as a result. This is an exchange in momentum in the system. And so the reaction wheel controls the roll axis, but it is not strictly necessary. So like, we're not going fast enough that we get crazy aero torques that roll the rocket. We get little ones, and the only reason the rocket would roll is because of those little tiny, very hard to predict disturbances. And I would say 70% of the time, it isn't a problem when the rocket rolls just a little bit. It's that extra 30% of the time. Sometimes these F-15 rocket motors, I think something happens in the nozzle where they do a little bit of channeling in the clay, and that results in the rocket spinning up quite a bit, because it's not a very strong force that spins the rocket up. It's just that the mass moment of inertia on that roll axis is so low that it's very easy to spin it up, and past a certain speed of like rotation rate, you start to lose your control authority, or at least lose the quickness of your control authority. So with this covered, I figured we should take a look at some of these flights. So this is flight one. It has a little bit of a delay here, but we'll watch it a couple of times. So we go up, motor is pretty wiggly, come down, light the motor, get out the legs, and we do a beautiful little flip. So that aluminum or silver shiny pad that's next to the launch pad, that is our landing pad. So the goal was to land 2 meters to the right and no meters back and forth, basically just pivot over and come down. So the wiggle on ascent is a control and modeling problem, but it's also a hardware problem. This is still while we were using the 3D printed TVC mount. And when I talked about how having no backlash and no slop in the system is important, it's because of this wiggling. Essentially, you get into a ringing phenomenon. You hit this like mode that can get excited in the whole system, where it's like you just feed back and wiggle the motor more and more and more. And because we're oscillating about the point that we want to be gimbaled to, it actually doesn't affect our attitude much. It's happening so fast that like it's kind of a silly looking thing. It doesn't affect our attitude that much, but it does ultimately like affect a little bit about how good the control is on ascent, and then it sets us up for a really tough problem, which is reorientation for the landing burn. And we'll get into that in a little bit. So this is flight 2. The changes here are that we're still using the same 3D printed mount, but the control software is a lot more tame on that mount. So the ascent looks a lot smoother on this, and then the landing, less so. So one of the big problems with Scout is in an effort to conserve mass, I got rid of any type of aerodynamic surfaces at the top of the rocket. Because if you watch this video, as it descends, it's already starting to drift to the side a little bit. And then when the landing motor comes up to thrust, we're fighting a couple of different problems, right? We're fighting our current orientation, which we don't have control over. We have a really low center of mass because it helps us with landing. And ultimately, if we were going fast enough, it would keep the vehicle stable and upright on the way down. But because that time window is so short, we never realize that stability, basically. So when the rocket is coming down, we're fighting the current attitude. We're also fighting the current rate, which is pretty easy to null out, the attitude rate or the rotation rate. But really, a big problem here is that we're trying to get back to a landing pad, and we're like at this point 4 or 5 meters to the left of where we need to be. And so the rocket pitches really hard to try and get back to the landing pad. That's why we adjust our attitude so aggressively on the way down. And you can make tiny assumptions about how the rocket you can make tiny assumptions about how the rocket gets back to the landing pad, so long as you end up close to over the landing pad on descent. So like, I don't have limits in this software that say, hey, if you're 50 meters down range, don't try to pitch crazy hard toward the landing pad, because you're going to spend all of your thrust sideways and none of it slowing yourself down vertically. And so what happens here is, because the control software is so tame and so damped on the way up, we actually drift to the left on the way up, and then we can't recover. So that's flight 2. Excuse me, 1 second here. This is flight 3. Flight 3 also uses a landing pad, and this is the first one with a metal TVC mount. And there's a couple things that happen here. So we have a much better recovery on this one. We do quite well on the way down, and we do quite well on the way up too, but it's that in-between period, that uncontrolled portion of the flight, that's really tricky. So as soon as we burn out, look at how much this rocket tilts. We burn out and it is just tipping there. And so by the time we light that landing motor, because of the thrust curve of the F-15, we're spending that 30 Newton spike just trying to recorrect for our orientation. And that's going to have a big effect on our altitude over time. It's going to have a big effect on where we end up. If we have to spend that 30 Newton spike pointed in a direction that doesn't work for us, we don't really have an option to correct for that. Again, I think having no aero surfaces was probably a mistake for this, because it would have really benefited from being able to just stabilize a little bit on the way down. And the other thing here that's a little deceptive is I do have a function that at the very end of the ascent burn tries quite hard to null and cancel out those attitude rates. But it never seems to work that well. And honestly, it's something I wish I had a better answer for, but something never worked that well with it. So let's move on. Let's go to flight 4 here. This is flight 4. Okay, here we go. So this is flight 4. This one looked great until the very end. Really smooth. At this point, we're no longer using a landing pad. At this point, I've realized that because of how uncontrolled we are in that mid portion of the flight, we shouldn't try to use a landing pad. We should just try and get down to the ground, touch the ground, and wherever we land, and we hope it's not one of these like lights that light up the pad. We hope it's not directly on top of the launch pad. And statistically speaking, it's like probably never going to be there. The problem here, though, is that the legs don't come out. And this is a little bit of an issue with how I deploy the landing legs, because there's this little nichrome wire that burns a rubber band. It's inherently a tricky process to get it to be the same every time. It's like a pyrotechnic device. By testing it, you lose the device, right? Once you test a black powder charge, you lose all that black powder. So you can measure the same amount of black powder, you can measure the same amount of resistance wire or nichrome wire, uh, but it's never going to be quite the same each time. And this one, we played it a little too close to the chest. It could never get those landing legs out. And honestly, we hit the ground fairly hard anyway. So it wasn't going to work out, but it did set the stage for flight 5, which we're going to look at right here. So this is flight 5, and I've got this playing back in quarter speed slow motion because it is glorious and wonderful. So we have a really clean ascent. Once again, that dawn sky just looks beautiful here, and it makes the F-15 look a lot more intense than it actually is. So pretty good ascent. We slide to the right just a little bit, but very good control, very tame control. And this is our coast period here. Once again, would benefit from some type of control during this period, but wasn't too bad on this flight. We have our landing motor that comes up to thrust, and as it's coming down, I want you to look at the bottom of the rocket and look at the sparks that come out the side. And so that's our throttle mechanism working. So the sparks, they come out the side because the rocket is trying to get, I mean, exactly what happened there. It's trying to get our thrust to match that descent curve so that we can touch down on the ground. And it necessarily means that some of these touchdowns are going to be really hard because we want to time it perfectly with the burnout of the motor. So some of them are going to be really hard, and some of them are going to be just like a picture perfect touchdown. So we're going to let this replay here. All right, here we go. We've got liftoff. Think of what else I can tell you about this flight. Yeah, I mean, it was it was a really good day. I don't know how to talk about it, honestly. It was a really good day to finally have this project completed after all of the work that went into it. But yeah, here we go. We got the landing burn. You can see the ascent motor gets ejected. The landing legs come out at just about the right time, and we come down at a little bit of an angle. One thing that I also was never able to totally solve in the program was dealing with the final portion of the burn. Something would happen in the control system at that final part of the flight that I could just never fix all of the bugs in it. And so there would always be like a little bit of attitude error at the end where the rocket knew it wasn't pointed in the right direction and it was generating the commands to point in the right direction. But something between that phase of generating the commands and actually realizing them, something didn't work there. And so with flight 5, I think we can probably watch it one more time if you'll indulge me here. And then there's one more flight to watch, and that's flight 6. We actually did 2 more, so 7 flights total, with the 6th and the 7th having really similar configurations to flight 5, just to see how reliable it was. And while flight 5 looked great and flight 6 and 7 were also quite close, I could never stick it again. So this is the only time that it actually landed upright and didn't tip over. But I think, it depends how you want to count it, obviously. Each flight had good throttle control. Each flight did get to the ground safely, and this rocket gets reused every time. So depending on how you want to count recovery, it landed perfectly at least once. So this is flight 6 here. Flight 6 is also playing back in quarter speed slow motion. Same thing as flight 5, really good control on ascent. We've got actually the drone in the background. You can see it there. A common theme with these flights is that I'm filming from like 30 different cameras. If you've seen my YouTube channel, you know that. But I never want to miss an event. So flight 6 has a really clean ascent. And once again, we tip over just a little bit in that uncontrolled portion of flight, but not too bad. We get the ascent motor out. And I think this is actually my favorite descent, just it coming back through the plume here, getting the landing legs out. If you look really close over here, you can see the rubber band flying away. And flight 6 would have landed had it not been for the bounciness of the legs. This is like the heartbreaking part about this project is I think if I had put more effort into the legs, we'd be sticking this thing half the time at least. But c'est la vie. It is what it is. You live and learn. So yeah, one more time on flight 6 here, and then I think we'll probably get to some questions. Yeah, I wish I wish we could figure out the coast period, and I wish we could figure out the landing legs a little better. Um, but yeah, here, look up just to the left of the rocket here, and you'll be able to see the rubber band fly away after it burns. There it is, right there. And then we touch the ground, we bounce, and that bounce is enough to tip us over. Um, this is I've said this thing for a little while, which is that I think a rocket that is 3 to 4 times as big as this would be a lot easier to land than this scale. So this is about a kilogram. It's really lightweight. It's really tiny, and it's it's just it can get knocked around really easy. If you get a 2 mile per hour wind, it's going to feel all 2 miles per hour of that. The other reason we fly at dawn is because I just wanted completely still air. Dealing with wind with a rocket that is this lightweight and this weirdly balanced in terms of mass, it was a pretty tricky thing to do. So I'm going to let this play out. But if you have questions, I would love to chat with you about any questions you have about the program. And yeah, thank you everyone for joining me here. And I think there's already one question that we can get to. I'm going to go ahead and move to this. So I'll start with Ron's here. What are you giving to the National Air and Space Museum? Well, I don't, I don't have any plans right now to give Scout to the National Air and Space Museum. But I do think it would be cool to do something with the rocket. It's just sort of sitting in my back room right now, pretty much unchanged from before. But I think it would be pretty cool to do something with it. Are you going to be using the Loki 6-inch Q hardware for the space shot motor? So the space shot is an ever evolving situation right now. I'm trying to do as much of it myself as I can. And so I want to build my own motors, but I'm still sort of in the phase where I don't know how much of it I really can do. So right now I'm building an O motor. It's a 6-inch O motor. I'll have a video about it on the channel at some point, so hopefully soon. But we poured the motor, we mixed all of the propellant, and you know, I've got a case, I've got a liner, I've got the closures, the O-rings, all of these things that you should need to build a motor. And the reason I'm doing it is mostly to see like, okay, how hard is this? Because it seems like propulsion is really, really difficult to get right. And also, you know, it's a fun challenge. You don't do a space shot because it's easy. And honestly, it's kind of a vanity project, right? You do it because it's like the glory of doing it. But I would like to try building as much of it as possible. I haven't looked at the Loki 6-inch stuff, at least hardware wise. But I have found that it is pretty difficult to get a reliable 6-inch diameter tube with, you know, not paying a ton of money. Basically, if you order stock material for a 6-inch diameter motor, like the chances that you actually get a 6-inch tube are quite low. Okay, Jason says for development, oh, I should probably mark these as answered. Here we go. For development, a short and quick flight makes sense. Any expected extra challenges when flying higher and thus descending for a longer time? Yeah. So if I were gonna restart the landing stuff, the way that I would want to do it is to send the vehicle really high up so that we could reach a terminal velocity. And that way, the energy that you're coming in with is relatively the same flight to flight. But you want to, I think it would be easier if the rocket were coming in at a pretty well bounded, like, this is going to be the speed that you light the motor. Um, but otherwise, for like high altitude stuff, I think like even this cardboard airframe could probably do a decent speed before it becomes a problem. I would try to get rid of some of those button head screws. You can see them here. They get pretty draggy. Those legs are really lightweight, and it doesn't matter. You know, drag isn't a big deal at this scale, but that would become a problem for sure. You know, I think the biggest challenge is at this scale just working within your mass budget. You have about 1,000 grams that you can work with, maybe 1,100, and so you make a tiny decision like, I want to switch to turn on my flight computer, and it costs you 10 grams. So like there isn't a switch. I just take two wires and I bridge them together, And as you scale up, I think a lot of those problems should get easier. Um, yeah. Okay. Here we go. Frederick says, oh, hold on, cancel. Here we go. Would using redundant sensors, two GPSs, two barometers, et cetera, and averaging their measurements help with accuracy combined with Kalman filtering? Yes, they would. I think like to a point though. I don't know how the math works on this. I think there's definitely value in having multiple sources of truth, or multiple estimates of truth. So multiple IMUs, multiple barometers, all of that is all well and good. I think especially having multiple barometers placed in different locations on the vehicle, because there's like a little bit of pressure buildup with all of the holes that are cut in the side here. There's like sometimes weird pressure things that happen, but frankly, you can do most of what you need to do with just integrating the IMU. So if I were doing this again, I think I'd probably ditch the GPS. I'd keep the barometer, and I might add a nicer IMU, or two. All right. Although the successful integration of these systems into a single model rocket is already very impressive, do you have plans to simplify this? And if so, how? Like more or less hardware, software? Yeah. Okay. So actually, this is a great follow-up question. I would ditch the GPS. I would get rid of that. I would build a much simpler and more lightweight computer. Ava, on the scale of this rocket, these four screws right here, Ava takes up like all of this space. And you just don't need a computer that is that big. You need a couple of pyro channels, an IMU, a processor, and then the ability to like log data. I definitely didn't need the telemetry. That could have been ditched. I have a camera up here. The camera feels like critical for me because I'm all about getting really beautiful looking shots. But yeah, there's a bunch of stuff that you can cut. I think the reaction wheel is probably not needed. You just accept like a little bit of a gamble on that. But I think those are the things that I would mainly simplify. Okay, what is the center of mass of the lander? Great question. So the CM on this is, if I remember correctly, it's at this like top set of screws here. So if you can see where my mouse is, actually this camera is kind of pointed at it. The CM is about here. And we want it that way because as you touch down, as you can imagine, the lower your CM is, the easier it is for the vehicle to like plop down and stay on the ground. And so the whole top section, apart from the reaction wheel here, the whole top section of this rocket is an empty tube. Like the nose cone is hollow. The only thing in the top here is there's a piece of paper with all the names of the people who support the project on Patreon. I flew them all on this flight. But yeah, the CM is as low as I could get it, basically. The only reason it couldn't go lower is because then it starts to interfere with the thrust vectoring mount. All right, there we go. Do you plan on doing any more propulsive landings? Yeah, so I have a couple of things coming up. The first is I am building a model of the SpaceX Starship. That's going to be a little while to actually put together, and it would be really fun to try and propulsively land that. I'm very skeptical that it can be done. Not at the real scale, but I mean, like, I don't know that the math works out for a model to do that, but I think it would be a fun challenge. And then I don't know. I mean, depending on how the space shot stuff goes and where the project is at, I do really think like building a version of this that is 5 times as big, and we can fly it out at Friends of Amateur Rocketry. We can fly it at an experimental site. I think it would simplify a lot of things, especially like having a LiDAR would be great. That would close a lot of the gap on the way down. Is having a good LiDAR. Okay, here we go. I know you've mentioned Big Scout in passing, but in a couple of years, would you do Scout G? G obviously meaning giant. Yeah, yeah. I think I may have already answered Matthew's question here, but yeah, if I do another one of these rockets, it's going to be bigger, and we're going to ditch the Estes F-15 motors. We can probably do like, if it still works out to do solid motors, I might do like a boost stage that just falls away. And then we basically land the second stage. The second stage spends all of its propellant to just land. But no, that's totally in the cards. All right. Will you be releasing code open source for incorporation into ArduRocket? Is ArduRocket the thing? Have they done that yet? Um, Either way, I am probably not going to release the code on this. Part of the reason is it's kind of a mess. So a lot of the way that I do control systems for this type of stuff is I come up with a bunch of arbitrary polynomials. So like 90% of the control system of like where this rocket needs to go and where it's pointed and what it needs to do is polynomials that reference obscure spreadsheets of a bunch of data. And so it's kind of it's a really bespoke solution to a problem that if it were to be released, um, would I think just like you're kind of better off starting clean slate. I think. Um, okay, was it hard to turn down your original goal of industry job offers to keep pushing along with VPS space? Um, well, fortunately, I never felt like I really had to turn down offers. I got one offer from a company that wanted me to move to the middle of Texas. In 2017 or 2018, and they wanted to pay me a rate that felt like it would be extremely difficult to survive on. And that was the only real offer I got. And then I got through a couple of rounds of interviews at SpaceX a while ago, and then I think I failed the technical, or I definitely failed one of their interviews. They started asking these interesting esoteric questions, and I definitely didn't give them answers that they wanted. But yeah, no, I have a lot of fun doing this. It's a very strange job, and I don't expect it to last forever. I kind of think like as long as people are supporting the project, I will keep doing it. But I don't think it'll last forever. And at some point, I would really like to move toward um, maybe a slightly more stable aerospace job, but we'll see. So long as people enjoy it, I will keep doing it. After landing, does the throttle clamp down completely to minimize thrust and make bouncing less likely? Great question, Thomas. Yes, it does. Yeah, as you can imagine, if you land and your rocket motor is still burning, you certainly don't want to go back up. And so there's code in there that detects when the rocket has landed and then just slams the arms shut. And the interesting thing is, how do you detect that you have hit the ground? So there's a couple of ways, right? If you don't have any like wheel on ground or feet on ground sensors, like a little micro switch at the end of the leg, you have to look at your inertial data. And your initial guess might be, okay, like look for a big deceleration event, right? If you're coming down, look for a big bump axially. But the trick is you have to have a really high sample rate for that to work. So it's possible, and this has happened, Armadillo Aerospace, if you guys know them, they actually had a problem with this once. But if you miss that spike on your accelerometer for whatever reason, because your sample rate is too slow or because the touchdown was softer than you think, if you miss that spike, it's a big problem. So how else could you detect that you have touched the ground and are moving back up? And the interesting answer is it's your angular rates. As soon as you touch the ground, the likelihood that you touch with all 4 feet is essentially 0. So when you hit the ground, you're going to tip in one way or another. You're probably just going to like tip a little bit. And as soon as you see it, and because you have a control system that's working really hard to keep the rocket very tame and upright, you can tell when you have a big outside disturbance like that by looking at your angular rates. And so it turns out if you set the limit at like, hey, if I'm rotating faster than 30 degrees per second, I have probably touched the ground. And so that's how that code works. But I think it's really interesting that I found that the most reliable thing to detect landing was your angular rate and not your altitude estimate, not your axial acceleration. It was that angular rate. Can you explain more how the anti-roll device works? Sure. So basically, your rocket is spinning a little bit, and think about me in this like chair, right? If I'm spinning in the chair, I like spin another device that I'm holding, I can exchange the momentum of me in the chair by putting that momentum into the device that I'm holding. This is called a reaction wheel. There's another version of this called a control moment gyro, which is not the same thing, but it is kind of close. And so this happens a lot on spacecraft, right? If you want to point your spacecraft in a different direction, you spin up a wheel and it creates a torque on the spacecraft to move it around. And because we only need one axis of control, what we do is we basically just put a wheel flat inside the rocket. And then when the rocket spins, we spin up the wheel in the opposite direction, and it sort of just gently turns the rocket. And that's how it works. Okay. Joe, please reserve one of your flown rockets for the National Model Rocketry Museum at the Museum of Flight in Seattle. Can do. Yeah, I mean, I'm not taking any of these apart, especially not Scout. I think it's best in its existing form. I will preserve it. Any plans to experiment with grid fins? Yeah, man, grid fins are awesome. I think if we do Scout G, or the big version of this, if we get some grid fins on there, like I feel like it's worth doing just for the looks, even if it doesn't work quite as well as like planar fins or whatever. Just for the looks, it would be pretty cool. Um, do you have flight 5 or 6 handily available that you could show us in real time? And that you might have mentioned this earlier, but what was the average altitude of these flights? So Casey, I don't have the footage that is super easy to pull up in real time, but I do have, just because of the time we have left, I do have a ton of stuff on the YouTube channel where you can definitely see it there. So there's a bunch of videos about flight 5 and 6, and there should be some real-time footage for both of them. Um, yeah, it should be on there. And then what was the average altitude? This is the point where you find out that this is more of a drone than a rocket. The average altitude was like 23 to 25 meters. So these things are not going very high. They're not going very fast. I mean, that coast period is kind of pitiful. It was the short time period is what lets these flights work without aero control at the top. But man, they do not go that high, and it feels real silly to go out to like this big, massive open desert and like set up in the dark, and it's done, and then you fly the rocket. It's over in 10 seconds, and it only went up a little bit. But that is the way the cookie crumbles. All right, a couple more questions before we run out of time here. The question, no question, just want to point out that the arbitrary polynomials would be an astounding band name. What's up, James? Yeah, that's a great band name. I like that. Joe, the Museum of Flight in Seattle has asked me to donate my TVC Atlas and Delta Heavy for an exhibit around innovations in rocketry. I am not including the Signal R2 with the donated rocket models. Your stuff should be part of the exhibit. We should talk. That is a great idea. We could totally arrange to get them a kit or a flown rocket or something like that. I think it would be that would be worthwhile. Nicholas says, "Are you ever going to fly the Falcon Heavy a third time?" Unfortunately, not. So the Falcon Heavy is a 1/48 scale model that I built, and I flew it twice, and both flights were, had a varying degree of success. But it won't fly a third time because I don't have all of the parts for it anymore. When I moved from Nashville to California, I did not keep all of the parts for the Falcon Heavy. It also it would really benefit from a rebuild. Frankly, the rocket was a very strange build. Okay, if anyone asked during my talk this afternoon about TVC scaled models, are you currently selling the Signal R2 kits? So the Signal R2 kits are no longer for sale. They are not currently being sold, at least by me. And it's a little too bad. I have a limited amount of time. We tried to hire someone actually last year to sell the kits, because I know that there are people who want to buy them, and I don't want to just say sorry, I don't want to do it. So we tried to hire someone last year, and I've tried to hire a couple of people at this point to run that side of the business, and it has never really worked out to get that to work. But I am not currently selling them, unfortunately. And I think that is all of our questions here. Make sure I check the chat here. Yeah, I think that's it. So thank you everyone for joining. Looks like we've got our time pretty much all set. But I appreciate you being here and hanging out. And I'm stoked. Hopefully I get to come back next year, and maybe we could talk about some space shot stuff then. Or who knows, maybe we talk about the big Starship model, or whatever else is going on. But thanks for your time. I hope everyone enjoys the other talks that are happening today. And yeah, I'll see you all around. Happy NARCon. All right. Give it a second before I hit stop broadcast. And all good.